We're going to start in about 30 seconds. This is just a sound check. Are you guys able to hear me? If you're able to hear me, please raise your hand. Excellent. Hi, everybody. I want to say that this does have a YouTube Live component, but the primary focus of this course is actually for the Carnegie Mellon University PhD level students. So in fact, I'm mainly going to be talking to you guys. There may be other people watching at the same time. If so, you're welcome. But this is really a class for the students that I'm teaching. If there's any point, students, you guys are all in the Zoom session. So if there's any point that you want to ask a question or something, please raise your hand. I do see there's a bunch of hands raised right now. I wonder if that's just because they're left hanging. What I'll do is, if you don't mean to have your hand raised, please put it down. Otherwise, if you have your hand raised, I want to quickly hear from you because we might have some kind of a sound issue. Oh, this works. So I see that people are putting hands down. I still see, oh yes, okay, almost all down. Great. Okay, so that means that this works. So we're going back and forth. There is about a 10-second lag between when this video is captured and when you guys get it. Just pretend that you're on the opposite side of a football field. Well, we'll do our best. So welcome to, I guess, Carnegie Mellon Online. I want to just start this class by reviewing a few things that we were talking about before the spring break, because it's been quite a while, and not only has it been quite a while, there's been a lot of stuff that's happened in the world. I don't blame you if you haven't been thinking about this stuff recently. And again, the way that we're going to run this class is that it's just like a lecture. If you have any questions, just please raise your hand in the Zoom, and I'll be looking for those blue hands. Let's see. Gee, I wish this Zoom would sort by hands raised. That's really annoying. Huh. Okay, this is just my own observation. Somebody, hopefully one of you knows somebody who works at Zoom, given given the people who go to CMU, maybe someone works at Zoom. If there's a way to sort these by hands raised, that would be awesome. Okay, anyway, we'll just deal with it as it is. Okay, great. Let's get started. So I want to first review this epsilon regularity because we want to try to move towards proving one of these famous theorems today that has to do with the extremal number of a certain graph. So epsilon regularity, let's remember, there's a definition. Oops, sometimes my pen has an extra bit over there. Definition. Epsilon regular for a pair of two sets of vertices means that if I have two sets of vertices, let's call them A and B, it means that for every subset, A prime, which is a subset of A, oops, I must say it is much easier to write with chalk on a chalkboard, but we'll make this work. And for every B prime, which is a subset of B, well, what we need is that the edge density between the A prime and the B prime is about equal to the edge density between the A and the B. And over here, when we say about equal to, that's where we have this up to plus or minus epsilon. I guess one good thing about this is that it's easier to get colors. Okay, so up to plus or minus epsilon. But this is not quite right. Actually, as you know, there's some other condition we need to write. Can someone remind me what's the other condition that we also need? This is not true for every subset A prime of A. This is true of certain subsets under certain conditions. What do we have here? I just want to review because then it's more interactive than just me simply talking the entire time. What should it be? There's something missing in the definition. Oh yes, if you have something that you'd like to add. Oh, I see. You have to, yeah, I see. I heard Tzu Chao, you have to indeed, I guess, what's the best way to do this? I see that there's one way which is to just go ahead and talk. Another way is if you raise your hand. I would prefer the raise hand method because then at least I can see the flags of people raising hands. I'm also going to give another feedback. I already can tell that when people are listening without headphones, then there's going to be this like background sound in the back. But anyway, I still heard Tzu Chao say the important piece, which is that, what we need is for every A prime in A, where the size of A prime is not too small. It has to be at least epsilon times the size of A. And for any B prime in B, where the size of the B prime is at least epsilon times the size of b, then this is the case. Yes, and again, an encouragement as you do all of these Zoom lessons with people, it's a lot easier if you have headphones. I will say that I even tried using headphones to do this Zoom call with you guys, but unfortunately, because I'm standing up, my headphones weren't long enough. So I just went and got some wireless ones, and hopefully that will come by next week. But so this is what epsilon regular means. And the idea here is that this resembles like a random graph. It's that somehow, even if I took some subsets, which are, like around here and A prime, and maybe this one, they can be different size, and take a B prime, then the edge density between them is about what we should expect. Okay, well, this has an immediate consequence, which is what we want to use for a lot of today. So let's go with the corollary. Whoa, sometimes there's a little bit of extra in my pen. A little bit of corollary. The corollary is that if you have any particular subset of, say, the B, then, which is not too small, then most of the vertices in A have about the right degree, the right density to B. So let me just write that like this. For any B prime, which is a subset of B, where the size of the B prime is not too small, at least epsilon times the size of B, as long as I have this, at least epsilon times the size of B, then almost all of the vertices of A have the right density to B prime. Can anyone tell me what almost all means? If you just raise your hand, if you can tell me what almost all means. I just want to make sure that we're remembering all of these various things that we're learning. Oh, this is interesting. So now I'm seeing that this is a little bit delayed. So Philip, yes, Philip, could you go ahead and let me know what you think? I see that the 10-second delay is now not going to work very well. But Philip, go ahead.
Sorry, all but 2 epsilon of them.
Right, thank you. And actually now I also see that the delay is not going to work. So I have an idea. The idea is that when I ask something, don't bother raising hand. Like if you have an answer, just please go ahead and say it. And what I'll do, as I do usually in class anyway, is I'll hear these ideas coming from the class, and I'll go ahead and use those to synthesize something. Okay? So that way we'll avoid this back and forth of 10 seconds delay. So what we have here is that, where this is true, all but at most 2 epsilon fraction of the vertices of A have density, within plus or minus epsilon of what it should be. Let's call it DAB plus or minus epsilon. So they all but this many fraction have density within this to B prime. And this is a very important corollary. This thing makes it so that, not only does almost every vertex have the right density to the whole B, but actually, even for little bits of B, this is also true. So now I want to go from this to prove the thing that we had talked about very quickly at the end of the last class, which was right before the spring break. And that's going to be the main tool that I want to use to prove something else. Now, this particular result is important enough that I want to make sure that it's clearly understandable. And so even though we talked about it very quickly at the end of the last class, I want to kind of go step by step through it here. So the problem is something like this, and maybe we can call it, it's an embedding lemma, but I'll just call it a proposition here. Okay, so the proposition says that if I have R blobs, R clusters of size M, so I'm given R clusters of size M each. Okay, so I'm going to draw a bunch of clusters. The key ideas inside this statement are that we want to say that between all of the pairs, they're all epsilon regular, and also between the pairs, they have at least a certain edge density. So given R clusters of size M each, and if I know that all pairs are epsilon regular, and I won't write the and, let's save some space, and I'm going to put a new thing that I didn't put on the last class right before we went on break. I also want to say, and all pairs have density at least some delta. Okay, so now I'm actually going to enforce a minimum density because that's going to help me to go and prove that I can find a nice structure inside. So given all of this, I want to say, then there exists, I'll call it a K, R, 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 where the number of these is T. So, oh, actually, no, I have it backwards. Let's do a K, T, 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 T with R of them. Okay, so this is going to be a K, T, T, T with R of them. And what we're looking for is we're looking to find T vertices in every single blob. But I left a lot of space here because there are some conditions that we're going to have to put on the R, on the T, on the epsilon, on the delta, maybe even on the N, we'll find out. But the way I always think about this result is if you happen to have R blobs and things are behaving pretty well, meaning that, we have the right density, at least a certain density between pairs, and also you have this very strong epsilon regularity condition, then you should be able to find something like this. Okay, so now let's go ahead and start trying to prove this. And to prove this, we need to show how you would go about finding this object. And the proof is actually quite natural. Let's just go over here. Proof. I'm going to draw the picture. So I have this, I have this, I have this. I'm drawing it big so that maybe I can put some more points inside. And maybe here's where I also want to put some more, maybe a little bit more participation also. It's like, how does this start? I need to go ahead and start finding a vertex. What should I do before I even pick a vertex? And here, you don't need to raise hands. If you feel free to shout out, I'll actually quickly capture that and continue talking with your idea. Exactly. Get rid of the vertices, which have the degrees which are too low. So in particular, what we have here is we have all these blobs. We have R of the blobs. I want to start by picking the first vertex for that first blob. And the way we'll do that, to pick that first vertex for the first blob, is we want to make sure we don't pick a vertex who has degree which is too low to any of these other blobs. And so for that, we cut out a bunch of vertices from this top blob, where cutout doesn't mean we're actually making the blob smaller. It just means let's not pick from there. Okay? So the first step is to cut out a bunch of these, and I'll write it like this. First step. It's to ignore. Let's be precise now. Let's ignore up to, it'll be 2 epsilon for each one, times R minus 1, because there are R parts, 2 epsilon times R minus 1 fraction of the vertices in the first cluster. Okay? And what we do by ignoring these is, then all of the vertices that we... Oh yes, question.
Don't we just need epsilon R minus 1?
Correct.
1/2 the epsilon is for degrees that are too big.
So that sounds like that was Liam who pointed out that, yes, you can actually improve this bound. In fact, that would be one of the things I'd have said later on. But it's that, I used the result that I just wrote earlier, which was the 2 epsilon. And indeed, there was a 2 epsilon written in, just a second, over here. There was a 2 epsilon written here. But what Liam pointed out is that, yeah, actually, if I only need to care about lower bounds, meaning that if I just need that the densities are at least a certain amount, then I can actually prove this corollary with just a single epsilon, not a 2 epsilon. And I would be able to say here, if I want to adjust this, I could, for example, get rid of the 2. And instead of this density D plus minus epsilon, I would say density at least dAB minus epsilon to B prime. So that would work. So let's go back here. And in fact, since you've said that, that is actually all I really need. I just want to make sure I don't fall through the floor, so to speak. I want to make sure that I still have density, which is at least something. So in fact, since you've said that, I'll get rid of that. I'll get rid of that too. Let's get rid of that here. So we'll ignore this many, and then now all remaining vertices in this first cluster, so all remaining vertices, all other vertices in, let's give the cluster a name, V1. I'm tired of writing first cluster. So V1, all remaining vertices in V1 are going to have the right density. So that means have density at least. And now what do I write? I'm not going to write D, V1, V2. Actually, this is where I use the fact that there's a lower bound on all of my densities. My lower bound was at least delta for the densities between large clusters. So I can write delta minus epsilon, density at least delta minus epsilon, to all other V, let's call them J's. Okay? So now I'm able to know that I have enough density. And then from that, just as before, what we did last time is let's just go and pick one vertex that's left. Pick any vertex. So maybe we'll call that step 2. Okay. Pick any vertex that's left in V1. Okay. So now that's going to be the first vertex, but I need to pick t vertices in the first blob. And so how I do that is I just go and say, well, there's that one vertex. Let's look at who its neighbors were in all of the other parts. Why do we care so much about neighbors? We care about neighbors because we're trying to build a complete multi-partite graph. And so from that one vertex that we've picked, that single vertex which I've marked with a 2, I'm going to have some subsets of all of the rest. So for example, there's a subset here. These are the neighbors. I'll write NBRS. These are the neighbors of that one particular vertex I've picked, and I'm just going to mark with the green a bunch of other ones. By the way, at this point, we've already seen that there's one inequality that has to be true. If we've ignored this much fraction, it better be true that that's not ignoring all of the vertices. So we're going to have some inequality that says we're not allowed to make epsilon times r minus 1 too big. At the end, we'll just look at all the inequalities and see what's left. But now we've got all of these neighbors. And so the next goal is to go and pick another vertex from V1, which I can use to continue this process. And here, what's useful is to pick another vertex in V1 that has enough neighbors in each of the other remaining green things, these neighbors areas. Because if I want a complete multipartite graph, I need that all of my t vertices that I pick are actually going to have the same set of neighbors in each of the other blobs. So we do the same step 1 again with another deletion. But now the deletion, I'll call step 3. Delete up to, now it's still going to be epsilon r minus 1 fraction of the vertices in V1, but here what we need is that we're deleting those vertices for which their density to each of these green areas was too small. So that's where we're seeing another inequality. Another inequality we need to be careful of is that the green areas are not too small. What does too small mean? Just let's see if we can, I want to see if people are still awake. So what would too small mean? When would I not be able to do a good job with step 3? Step 3, I want to say, these guys all have enough neighbors to these green blobs. When might I actually have a problem? If the green blobs are of size smaller than epsilon. Exactly. If the green blobs are of size smaller than epsilon, then you'll have a problem. Because remember, if I go back to here, my condition here only works if the B prime has size at least epsilon times the size of B. And so if I go back here, I have a requirement that the green blobs better be of size at least epsilon. So actually, let's start collecting these conditions. Over here, I already see that I need the green blobs of size at least epsilon. The green blob had size at least delta minus epsilon. So let's put a few more ands. So we needed that the green blobs all had size at least delta minus epsilon, and that needs to be at least epsilon. Sorry, when I say size, I mean fraction, size as a fraction. So let's just go back and look. Indeed, the fraction of the vertices that the green blob occupied was at least delta minus epsilon, and that better be at least epsilon fraction. And while I'm at it, let me also write down the other condition which we needed, which was that this epsilon times r minus 1 is not the whole thing. So let's put that here. We also need that epsilon times r minus 1 is not the whole thing. I'll just say like less than half will be enough. I mean, I don't want to say less than 1 because maybe there's some rounding error, but half will definitely be enough. Meaning that there's at least half of the blob left to pick those vertices in. Okay, but once I do this, I delete up to this much fraction, and then, great, I can do another pick. So I'll call this step 4. Pick any vertex left in V1. Okay? So then, if we do this, then what we have is the ability... Question, yes, please.
I'm still a little bit lost on why we're deleting the epsilon times r minus 1 fraction of the vertices in V1 again.
Okay,
Why are we
thanks.
doing that the second time?
So somebody's asking, why do we delete the epsilon times r minus 1 fraction vertices in V1 a second time? And the reason is because, and I'm glad you asked actually, the beautiful thing is that when you can ask these questions, then we can explain why every single step is essential. So now, why to delete those? It's because right now I know that every vertex, after deleting the type 1 guys, every vertex has the right density to the entire V2, the entire V3, and so on. But right now, what I'm about to do is I'm trying to build a K T. So I need to pick T vertices in each of the blobs V1. And when I need to pick T vertices in each of them, I actually need to be able to pick again and again and again, so that when I look at the second vertex, it has enough neighbors inside that green blob. Because you see, as I try to build this complete multipartite graph, the neighbors of the first vertex I picked are one green blob, right? It's over there. But then when I pick again, it has to restrict the green blob a little bit more, because I need to make sure that whatever I eventually pick in the V2, those are adjacent to both of the vertices that I've picked so far. So the reason I want to do the second deletion process is the second deletion process is actually deleting those vertices whose densities to this particular blob, this green blob, is too small, this green blob is too small, this green blob is too small, and that green blob is too small. So that's what that is about. So let me maybe annotate that, since that was a good question. So delete up to this many vertices in V1 so that all the vertices left have density, at least it's the original delta minus epsilon to all of the neighborhoods. So this is actually quite important because some people asked after the last class, am I, for example, making the density get smaller every time? Am I replacing the V2 by this new smaller V2? And the answer is no. Actually, originally, the whole V1 and the second V2, these whole things were epsilon regular with density at least delta. And because of that, because of the corollary that lets me apply to a B prime which is smaller, I'm able to say only epsilon fraction of the vertices in this whole V1 have a density which is too small to this little green piece, as long as I satisfy this first condition here, which is why we put the first condition here. And once you do that, now you can just go pick any other vertex left, and automatically what that does is that if I now look at who is neighbors of both of the vertices that I've picked, this gets smaller. So these are now the yellow pieces. And so the key from this particular piece, after we've done these 4 steps, what we have is now the number of common neighbors. Actually, let's not call it number. Let's do everything with fraction. So let's say every V2 up to V, how many V's were there? There were R of them. Every V2 up to VR has at least, it becomes delta minus epsilon squared fraction of vertices adjacent to both picked. Does this make sense? So this is now very powerful. It's that I could conceivably do this a bunch of times. And that's why we care so much about the corollary, which says that I can restrict to a B prime instead of the whole B. So as I keep doing this, what's going to happen? I'm going to run this all the way down, and at some final stage, I will have picked T vertices in the top, in the V1, and all of the other things have shrunk down. I first want to draw that picture, and then I want to talk about what that requires in terms of these inequalities that are here. These inequalities are only for stage 1. But let's draw what happens if we ran this all the way down to the last stage. So after doing this to pick T things in the top, eventually what we get is T vertices on top. So these are the T vertices that we've picked. And then what we have left for the other parts are, we have the whole other part as it was before. I guess I'm drawing them a bit large, and I guess now there's only 3 other blobs because I just want to draw bigger blobs. But this should have the same number of blobs with that as one of the blobs as we had before. So these are still V2 up to VR. Okay, so we're just drawing less blobs, but we mean the same number of blobs. And inside each of the blobs, I have restricted down to some smaller regions. Actually, here's a quick question while I draw this. Maybe somebody can shout out. How big, at least, is each of these regions? These are common neighbors of all of the T vertices I've picked so far. Exactly. I heard that each of them should be at least delta minus epsilon to the t. So now, all of the common neighborhoods are size at least delta minus epsilon to the t fraction of their original blobs, right? Of their original V whatever. Okay. Well, once I've got this, I should do it again. But before I do it again, let's write down what kind of conditions might I have needed. In order to get this far, what would I have needed in my constraints? Originally, I had delta minus epsilon has to be at least epsilon. But now what we're seeing is that as we're restricting and restricting and restricting, like the almost last step would have given me blobs whose sizes are not delta minus epsilon fraction or delta minus epsilon squared fraction, actually not even delta minus epsilon to the t fraction, like the step right before would have been delta minus epsilon to the power t minus 1 fraction, and that needs to be at least epsilon. So I've now updated my first condition to this. Second condition. What would I have to do for the second condition? Well, for the second condition, if you see what's going on, I eat up epsilon times r minus 1 fraction, and I do this t minus 1 times. So that means that I have another condition. Let's replace this, not epsilon times r minus 1, but I have to do it up to t minus 1 times, and that still has to be less than 1. I'll write less than half just to give myself space. So I'll write t minus 1 less than half. Okay? But if I have these conditions, I am actually able to run through the whole V1 and pick t vertices. And after I've picked t vertices, I now have this picture. So now I should just do this over and over again. Unfortunately, it's hard to draw what's going to happen inside here. But if you imagine what's going to happen, we're going to have to cut out. We'll have to cut out of V2 all of the vertices whose degrees to each of the remaining specialized neighborhoods is too small. But here I'm going to draw the cut out in an interesting way. You see, when I do the cutout, I'm not going to say replace the whole V2 with that. I'm not going to call that V2. V2 is still V2. So when I do the cutout, sometimes I'm lucky. And the cutout cuts out stuff which is not even in that tiny blob. I'm just cutting out all kinds of stuff. Sometimes it cuts out stuff in the blob too. But I'll go back to calling this, well, I guess we can call this step 5 just because over there we had up to 4. So I'll call this 5. Now what I do is I will let's use the word ignore, because I want to emphasize it's still actually V2. Let's ignore all the vertices of V2 that have density too small. Too small is less than delta minus epsilon to any of the other, let's call them blue neighborhoods. Blue neighborhoods. And so, again, the blue neighborhoods are already small, but if I'm lucky, not lucky, but if I enforce that these blue neighborhoods are big enough by removing the t minus 1 and replacing it with a t, if I do that, then indeed I can do this. So when I ignore this, each of them, I still have these usable as b primes for the epsilon regularity between the whole V2 and, let's say, V3. And so when I ignore this, I will actually cost myself up to epsilon fraction of the entire V2 every single time. I will do this now not r minus 1 times, but r minus 2 times. Okay? So we do this r minus 2 times because we say any of the other, there's r minus 2 of them. Maybe let's annotate that. R minus 2 of them. Okay. And then once you've done this, now hopefully there's still room to pick something else here. And that's already showing us that we now need to make sure that that tiny blue blob is still big enough to survive getting rid of these r minus 2 times epsilon fraction. Okay? So it's r minus 2 of them. Let's also keep the bookkeeping. After we've done all of this, we total ignore up to epsilon. That's supposed to be an epsilon. I'll try to draw it a little bit more clearly. Up to epsilon times r minus 2 fraction of V2. And it is true that sometimes I'm lucky and I ignore stuff that's outside the blue, but as long as I know that the blue itself was big enough, I'm okay. Because the next step I would do is just pick some vertex inside the blue. So 6, I'll use green. Pick any vertex in the V2. I'll write the blue part of V2, and then restrict again all of the rest of the neighborhoods just to whoever that vertex is adjacent to. Again, every one of these blue neighborhoods is already adjacent to all of the t things that we picked up there. So we now can restrict even further to just make sure it's also adjacent to the one I just picked. Pick any vertex and restrict all other blobs, all other blue neighborhoods to their neighbors. Okay? To its neighbors. Okay, and at this point, we also see some other constraint that we have to have now. We now need to go back to these blue blobs, and over here the constraint becomes, let me go back one more, over here the constraint becomes, it's not just that this delta times, sorry, just a second. So this one we needed in order to use the epsilon regularity, but this one over here now becomes interesting. The second condition was what happened when we said, well, when you go and pick all of those from the V1, there's still vertices left to pick. But now, what condition do we have to write? I mean, if you think about this, what we need is that when you go and take out r minus 2 times, when you take epsilon out r minus 2 times, you also need that epsilon times r minus 2. That's how many times we could potentially eat something up. That now needs to not eat up your entire delta minus epsilon to the power, how much was it? It was to the power t. Because the blue thing, all we knew is it's at least delta minus epsilon to the power t. So we need to have that this thing doesn't eat up the whole thing. So we'll say less than, let's put a 1/2 just to make sure we have extra space. Delta minus epsilon to the power t. Does this make sense? The basic idea here is that we're saying that we know that each of those remaining blue blobs has size at least delta minus epsilon to the t. The half makes sure that we still have more space after we have deleted out epsilon fraction r minus 2 times. So that's how this calculation works. Let's keep going. Maybe people can already see what's going to happen. Repeat, repeat, repeat. At some point, we pick out t vertices inside this tiny blob, the tiny blue blob, and we have further restricted all of the other blobs. So when I draw the picture, what we now have is that we'll have t vertices that we've picked on top. We'll have t vertices that we've picked from the V2. And in each of the other blobs, like this is a V3, all the way to a VR. In each of the other blobs, we have really, really narrowed ourselves down, and it's now pretty small. So again, I can't draw it too small. That's supposed to be even smaller than it was before, but I can't draw it too small because otherwise we wouldn't be able to draw anything else inside. But what we have here is these are now the common neighbors of everyone that I've picked so far, of all 2t. And so now, what kind of conditions do I have? How big is each of these blobs? Let me see. Feel free to shout out what you think it is. How big is each of these blobs? And I'll also write some comment. It's like, I'll start writing it, and hopefully by then somebody will say it. Now, each of these blobs, neighborhoods, has at least a certain fraction.
It should be delta minus epsilon to the 2t.
Yes, delta minus epsilon to the 2t. Thank you very much. It should have at least delta minus epsilon to the 2t, and I've picked all of these things over there. And now you see where this is going. So maybe let's pull back a few screens, and let's write down the updated new inequalities. So if we go back to these things and look at these inequalities, well, over here, I originally had that the delta minus epsilon to the t was supposed to be at least epsilon. But now the thing keeps shrinking and shrinking and shrinking. By this point, it's not just t. By this point, it's 2t. Actually, it's 2t minus 1. But I'll just go ahead and write 2t, because 2t is a stronger condition than 2t minus 1. Similarly, I'm going to update this pinkish-purple inequality. I'm not doing it just once. In fact, I'm doing it t minus 1 times until I grab that last one. So I have to have another t minus 1 here. But now you see what's going to happen. If I just do this all the way down, if I do this all the way down to the VR, what is the final condition that I'll need? So I'll say you just do go until you get t vertices in each blob, in each Vj, right? That's supposed to be a j. T vertices in each Vj. Once I got t vertices in each Vj, I want to know now, what are the inequalities that I need? I'm going to flip back to that slide. Right now, go ahead and shout it out, because by the time I get back to that slide and start writing, your audio will have hit. So let's go back here. And how would I know? I need to see how I update all of these inequalities. And the natural generalization is I'm going to give some more space while we're getting audio. Yes. Thank you. So that one goes to RT. We could save 1, but I'll just write this. This is enough. Bigger equal epsilon. And then also the pinkish purple thing updates. We now, what happens? Well, we also need it, where it's like epsilon. It's a funny thing. It's like it keeps going on and on and on. And in the very end, you don't even have the r minus 2. It's like you get a whole bunch of these all the way down to the last one. It's just an epsilon times t minus 1. That has to be less than 1/2 to the power delta minus epsilon. Oh my gosh, what is this? It's something. And actually what I'm going to write here is I'm going to write down, if I put RT, well, I guess we could look for a pattern. Let's see. I think we might want r minus 1. Is that right? It's like r minus 1 or r. It doesn't quite matter. But I'll call it RT because that's a stronger statement anyway. If I actually have this, I will definitely have whatever else I need. I mean, I could possibly write r minus 1, maybe even r minus 2. But if I write RT, I don't have to worry about it. So we'll put this here. We'll also put that here. And to really not worry about it, I'm going to put an r here as well. Because at this point, if I impose this yellow inequality, for sure all of these intermediate inequalities will be true, because the biggest the left part can ever be is when the multiplier here is like, it used to be r minus 1, then it's r minus 2. Let's just replace them all with r. And all of these have t minus 1, so just leave the t minus 1. And over here on the right side, like the smallest it could ever compress to is something like this. And once I've written the yellow thing, I can actually go and cancel out these two and say, let's just not even worry about those, because everything is superseded by the green and the yellow. And so at that point, that finishes this proof. The proof is that I've eventually been able to find the k t t t t t t t with r different parts, meaning there's t things in each part. And the only conditions I need are that the delta minus epsilon to the rt is big enough, and also that the epsilon is like somehow not ridiculously big. This epsilon times t times r is not too big. When you look at this, I'll say the first time I learned this, I said, this has too many epsilons, r's, t's inside it, and too many inequalities. What does this actually mean? So the way to think of this is whenever you are going to ever use this proposition, you're only going to apply it in a situation where the epsilon is pretty small. In fact, what you're going to try to do whenever you apply this thing is to say, I happen to have a really good, precise control on how epsilon regular this graph is, and for my delta is like bigger. It's not very interesting to say I have a graph which is 0.1 regular, like epsilon being 0.1 regular, except that the densities are all at least 0.001. That's sort of like someone telling you that you are, 3 miles to downtown plus or minus 5,000 miles. It's just not useful. So usually you want the epsilon to be really small and the delta to be bigger. So actually I've seen papers before. There are papers before which say things like, they'll write stuff like, we will use epsilon double less than delta double less than 1. This is a quite useful way of thinking about how you would ever apply this. The double less thans mean of smaller order of magnitude. And so over here, what we have is that the epsilon is the smallest order of magnitude, and then there's the delta, which is the next biggest order of magnitude. But in general, when you're applying these things, it's most interesting when the delta itself is not that big. Like you don't even want to apply this when the delta is big, because in some sense, if the delta is big, maybe there are other ways to prove the same thing. Now, if you look at these conditions, what does it mean? Well, actually, if you look at the first condition, if you actually make the epsilon really sufficiently small compared to the delta, the first condition is definitely going to be true. The first condition, of course, you have to think of how the r and the t play in to this double less than sign. But the bottom line is that if you use the r and the t in order to make this double less than sign, like epsilon really, really small compared to delta, then you actually are able to make the first thing true. So I'm just going to make a comment here that this first part, I should probably make the colors somewhat compatible. This first double inequality would give you that first line. So that would match most of the applications that we use. The second one, the delta much smaller than 1, that somehow, I don't know if that's as big, as obvious anymore, but I'll say that that's sort of what plays into this first one that we struck out, where we said the epsilon is going to be small. And well, if the epsilon is smaller than the delta, then and the delta is less than 1, much less than 1, then we definitely have that too. But in general, this whole set of inequalities does play into this last part, where we're basically saying that the epsilon and delta also satisfy some relationship. Although I'll say that what we have at this point, you could actually also get, I believe you can also get it straight. Oh, no, you can't get it straight. Yeah, so I will say that. You cannot get it straight just from that green line, because I do actually need that the epsilon and the delta are both much smaller than 1, since over here I just have epsilon related to... Oh, no, I take that back. Actually, you can get that straight from the other one too. Yeah, so you can get that one straight from the other one too. So I'll put that here. The only time you don't get it straight from the other one is when you only run this once. If you only run this once, then you actually will need the second one as well, meaning this line here doesn't include these extra multipliers. Okay. So what I wanted to show is that this particular lemma, every time you're trying to apply the Semeredi regularity lemma, we will generally get to a situation that looks something like this. And with a situation that looks something like this, then we will be able to find this k t t t t t t t. How do we actually go and apply this? I will do that in the next week's session. And the reason I want to do that in the next week's session, it's not next week's session, the next class session, which is on Friday. But don't leave yet if you're on CMU. The reason I want to save a few minutes at the end is because we're going to shut down the live stream for the outside world. We'll say goodbye. But then I'm going to switch into our Zoom meeting with the CMU people to sort of discuss what worked and what didn't work from this very first online lecture that we're trying to do in this particular class. So for anyone who was tuning in from the outside world, I hope you had some fun seeing what this graduate level mathematics might look like. And what we'll do is we'll see you again on Friday. But I want to use the rest of the time to discuss with CMU about what is the best way we can improve all of our online teaching. See you next time.